So we're going to talk today about a nucleophilic substitution reaction. Alright, so we've spent a lot of time talking about electrophilic aromatic substitutions, and here we're going to talk in this online mini lecture about nucleophilic aromatic substitutions. So I've shown an example of that over here in this reaction where the chloride substituent gets substituted with an OH group, so that's what I'm showing here. This chloride gets substituted, and the mechanism for this reaction is different from everything we've talked about so far. So this is not an electrophilic aromatic substitution. It is also not an SN1 or an SN2 type of substitution reaction, and we can go through the reasons for that. This is not an SN1 reaction because, as you will recall from our previous discussions of SN1 reactions, those require a positive charged carbocation intermediate. You do not actually form a carbocation intermediate in the context of aromatic substitution reactions because the instability of the aromatic carbocation. This intermediate that I've shown here is so unstable, so high in energy, that you do not form that, and SN1 type mechanisms cannot occur in aromatic systems. This reaction that I've shown, this substitution of chlorine for hydroxyl, is also not an SN2 reaction. And the reason why it cannot proceed via an SN2 mechanism has to do with the steric requirement for an SN2, which requires a backside attack of the nucleophile at the reacting carbon. Because of the sp2 hybridization of this carbon, you cannot undergo backside nucleophilic attack on sp2 hybridized carbons. That's always going to be the case, that it is never, you are never able to do that kind of backside attack on the sp2 hybridized carbons. That's going to be true for this. It's also going to be especially true in the context of carbonyl chemistry, which we will get to later on in this semester. So that's, we know it's not electrophilic aromatic, it's not SN1, it's not SN2. What kind of reaction is actually going on here? Well, let's go down here, scroll down and look at this mechanism. What you actually form in the first step is a nucleophilic attack of the OH minus on the carbon that it's going to be attached to. So this is a nucleophilic attack of the OH minus that generates this resonance stabilized carbanion intermediate called the Mesenheimer complex. Alright, this is the key intermediate formed here, where again this anion, this carbanion, comes from the lone pair of electrons in this double bond localizing here at this position. And then in the second step of this reaction, those electrons reform the aromatic ring. You push off the chloride, and you now have the net substitution of chloride by the hydroxyl, again according to the procedure shown here. OH minus attacks the chloride, you form the carbanion Mesenheimer complex, that then re-kicks off the chloride, and you end up with your desired product. Like electrophilic aromatic substitution reactions, these reactions also have strong regiochemistry preferences. And what I mean by that is they only occur if there is an electron withdrawing group in either the ortho or the para positions to the leaving group. So we can go through why that is the case. Here I've shown for the ortho substitution reaction, again the OH minus comes, does nucleophilic attack on the carbon that it's forming a bond to. The electrons in that double bond go and form an anion here. That anion, which results from the ortho attack of the hydroxyl over there, that anion can be resonance stabilized by its proximity to the nitro group. So again, if I push electrons into this bond, push those electrons up as a result, let's zoom in a little bit. Here, that gives me a resonance stabilized anion, where the anion can either be on this carbon or resonance stabilized way up on that oxygen. That resonance stabilization is only possible for this ortho substitution pattern. Then in the second step, that resonance stabilized anion will swing all the electrons back down. So you reform that double bond, push these electrons here, kick out the chloride, and now you have your desired OH product. We can see that for the ortho substitution, so when I have nitro group ortho to the carbon that's being attacked, I can also see analogous resonance stabilization for the para substitution product. So here the OH minus comes, attacks the chloride, we form an anion at this position. That anion can now be resonance stabilized at this position here, and also once it's at this position, the carbon that's directly attached to the nitro, it can be further stabilized by delocalizing through the nitro up to this oxygen. Okay, that's where that negative charge ends up. So again, this negative anionic intermediate now has 3 stable resonance forms, including the ability to delocalize the negative charge onto the nitro group directly. Then in the final step of this reaction, I push the electrons back down, kick off the chloride, and now generate the desired final product here. So this now has a resonance stabilized anionic intermediate. And again, if I have the nitro group at either the ortho or the para position, that allows me to access resonance stabilization that includes that nitro group. So that's what I'm showing over here. That is a resonance stabilized form that includes the nitro group. This guy here is a resonance stabilized form that includes the nitro group. Alright, so either of those positions, which include those nitro groups, are now able to better stabilize the Mesenheimer intermediate. For the meta substitution pattern, so if I have a nitro group here, OH nucleophilic attack on that carbon would generate an anion here. This anion, no matter how many resonance forms I try to draw for this, cannot end up on the carbon that has the nitro group, so it cannot benefit from this analogous stabilization, and as a result, it is not formed. So that's briefly what nucleophilic aromatic substitution reactions are. You can recognize if something is a nucleophilic aromatic substitution if, first of all, the benzene ring that's reacting has an electron withdrawing group. We're going to call them SNAR. That's substitution nucleophilic aromatic. You need a aromatic ring with electron withdrawing groups. And then the reacting partner has to be nucleophilic. So for the context of the EAS, the electrophilic aromatic substitutions, our reacting partners were clearly electrophiles. Here we're talking about an OH minus being the reacting partner. That's clearly a nucleophilic reacting partner that reacts with an aromatic ring with electron withdrawing groups on it to generate the desired products.